science enthusiasts. My name is Jason Zakowski. I'm a high school chemistry teacher and a science communicator, but I'm also the dog dad of Bunsen and Beaker, the science dogs on social media. If you love science and you love pets, you've come to the right place. Put on your lab coat, put on your safety glasses, and hold on to your tail. This is the Science Podcast. Hey everybody, welcome back to the Science Podcast. We hope you're happy and healthy out there. We got a great show for you today, but next week we're taking the week off from the podcast. Don't worry, there'll be content. There'll be recordings from Science Chat and Pet Chat from Twitter, but we're on vacation next week. We're going to be taking a week and a bit off from doing all of the things that we do on social audio with our shows on Twitter that are, Pawdcast to a bunch of different sites, and also the podcast. So I'm going to take a week off. We're going to the mountains, and we're going to be doing some stuff around Alberta, maybe going to the Badlands, checking out some dinosaur bones. I'm sure Bunsen will be happy if he finds a dinosaur bone. Okay, what's on the show this week? In science news, we have a super creepy story. So spoiler alert, it's creepy, and I'm not going to tell you more than that. In pet science, we're going to talk about cats, their litter box, and warnings to pregnant women, and how there maybe is some change coming around that. Our guest this week is Dr. Deanna Hooper, who's a cosmologist, and we talked to her about dark matter, but also the expansion of the universe. It's such a good conversation. She's so engaging to listen to. Hey, dogs, what do you call it when you have too many spiders in your house? A no-fly zone. Oh my goodness. That one's terrible. All right, on with the show, because there's no time like science time. This weekend's science news, oh man, we have a creepy story. It combines two creepy things, zombies and spiders, in a field of biology called necrobiotics. So, spoiler alert, the story is going to be about 4 to 5 minutes long. If this creeps you out a bit, you can skip right through to the pet section. Okay, I gave you some time to think about it. Some of you are so curious you want to listen. What is this story about? A team of researchers presented their findings in July in Advanced Science, and they found that they could reanimate a spider corpse with air, a syringe, and superglue. Okay, so why or how did they do this? A mechanical engineer at Rice University, Fei Yap, had a question that started this all, and that was, why do spiders curl up when they die? And that's a really great question. If you've ever seen a dead spider, they curl up. So why do they curl up when they die? And the answer is very simple. The spider forces its own type of blood into their extremities by pressure. And when a spider's dead, there's no longer that pressure to force fluid into their legs. So just like a deflated balloon, it curls up. And once they solved that problem, or maybe they just asked a spider biologist, because this is a well-known fact, this is where a little bit of the mad science and possible ethical gray area started. The scientists were like, what can we do with that? How can we use this? So the team started with a wolf spider, and their first great idea, if you can call it great, was to try to force wet air into it to see if its legs would unfurl. And they put it into a double boiler. It didn't work. So the second trial was a breakthrough. They stuck a syringe into the spider and superglued the valve, superglued it shut so there could be no air escape. And when fluid was pumped into the spider, the legs opened. And then when fluid was taken out of the spider, the legs closed. Now you might think this is interesting, but the team didn't stop there. They turned the spider into some kind of creepy claw game, and they could lower the spider with its crumpled up legs, inject fluid, the legs would open, decrease the fluid, the legs would close. And in doing so, they could grab stuff with this spider. There's more. You might think this story's over. It's not. The team wants to make sure that the spider body doesn't break down as quickly, because after 100 trials, the spider body was about at the end. And also, they want to control each spider limb individually. What is the application for a spider claw game? The team is learning more about biology and engineering, and the hope is in the future, a similar system could be made that uses the same biology as the spider. Obviously, the next time you're in Chuck E. Cheese, you're not going to see a tarantula being lowered down so you could win a Pikachu. And there are some like legit ethical reasons about using the corpses of creatures for this kind of science. If you take away the creepiness of it, from a science standpoint, it's interesting. Problem solved. Questions were answered. More research is being done. Now, the other thing that I'm concerned about is like a spider body is very brittle, so I'm not sure what they're going to be using it for if there's applications in the future. I think a robot body would be smarter, and perhaps one based on the spider anatomy. Okay, that's our super creepy. It's not even Halloween. That's science news for this week. This week in Pet Science, let's talk about how pregnant women should stay away from the litter box. Toxoplasma gondii is a legit concern for people that are expecting. Most pediatricians will warn not to come in contact with cat feces, and the reason makes a lot of sense. The T. gondii affects many warm-blooded animals, including a whole schwack of humans. We can contract T. gondii in a whole bunch of different ways, eating undercooked meat, contaminated meat, especially like pig meat, pork, but also coming in contact with cat feces. And infections with T. gondii for those that are pregnant and their unborn babies are particularly dangerous in the first trimester. Well, what can happen if you have a T. gondii infection in the first trimester? It's not great. There are birth defects and even death of the fetus, right? So it's not great. If you are not a fetus, if you're a person, you can also become very, very sick and even die from complications, especially if you're immunocompromised. So the whole staying away from cat litter boxes when you're pregnant, it's grounded in very good science. A team of researchers found an enzyme that could potentially be targeted that would take out T. gondii. And that enzyme is found in lots of things, plants, animals, and even T. gondii itself. It's called PPO. It's got a long name. I'm not going to say it. In plants, it helps with the production of chlorophyll. And in T. gondii, it helps produce heme. It's critical for the structure and the life of this organism. So the whole idea is you could potentially make a herbicide that targets PPO. And one of the cool things is that the PPO in T. gondii is very different than animals. So you could potentially have a herbicide developed that would target PPO, and it would kill the plants, and it would also kill the T. gondii, and it wouldn't affect the humans. There's already something out there called oxidizon. That's an inhibitor of heme in plants. So they looked at using that first as a therapeutic strategy with people that are affected with T. gondii in the lab. So this is not in people. It wasn't particularly effective. However, the team is looking at changing some of the molecular structure of oxidizon to be a better therapeutic to both wreck the heme and wreck T. gondii. There's some exciting developments. A synthesized derivative exceeded the efficacy of the parent oxidizon by 100-fold. They're getting better at changing this molecule ever so slightly to become more powerful in both a herbicide and affecting T. gondii. Now, the whole reason why this is important is that when people are infected with T. gondii, especially if it gets to the brain, there's not a lot that modern medicine therapeutics can do. So this is an area of research that could potentially be used as, I don't want to say a cure, but a type of medicine if you are infected by T. gondii, and especially for pregnant women who maybe do have a cat and are super worried about getting next to the litter box and worried about that infection. The team is very gung-ho about making a whole bunch of other derivatives and checking their effectiveness for treatment in humans. That's an exciting next step. That's Pet Science for this week. Hello, everybody. The Science Podcast will always be free to download and listen to. You'll never have to worry about paying for it. But we have some amazing ways that you can help us out with running the show. The first one is to think about becoming a patron on Patreon. And we call our patrons now the Paw Pack. There's a whole bunch of awesome perks and different tiers of support. We also have a very detailed and excellent merch store. And if you're listening to this in time, we have pre-orders of the Bunsen 2.0 stuffy that was just adorable. You can check it out. There's also the Beaker stuffy on our store and a whole bunch of comfy clothes. The third thing you can do is give us a good rating. Rate the podcast wherever you're listening to this. We'd love to get a great rating from you. Okay, back to the show. It's time for Ask an Expert, and I have Dr. Deanna Hooper, who's a theoretical physicist with me today. How are you doing today, Doc?
Hey, great to be here. Thanks for having me. Really, really excited to chat to you.
Oh my goodness, I am so excited to chat with you too. We're going to talk about gravitational waves and something called tensions. I have no idea, but we're going to get into it. But before we get there, Doc, where are you calling into the podcast from? Where are you in the world?
I am actually currently in Helsinki in Finland, so quite far east and quite far north from where you are.
A little bit north, though.
A little bit north from where you are.
Yeah. Red Deer, Alberta is fairly north as well, but I do believe Helsinki's further north.
Yeah, I think we might be about the same, actually. Yeah.
Yeah. Have you lived in Finland your whole life? Are you there for school? Are you a Finn?
So, no, I've moved around a lot. It's always a fun question of where I'm from. So I was born in the UK. My family moved to Spain when I was 6 years old. And in Spain, I did my bachelor's in physics and then decided to move to Germany to pursue a master's degree in astroparticle physics and cosmology.
Look at you go.
Then I stayed in Germany for my PhD in cosmology.
Okay.
And after getting my PhD and becoming a doctor, I moved to Belgium for 2 years for my first postdoc. And now I'm in Finland for my second postdoc. So the postdoc is just this stage somewhere in between getting a PhD and becoming a professor. And it's really fun because I still feel like I'm learning a lot of things. I get a bit more responsibility, but also I'm learning a lot of things. So it's this fun transition period. And I get to move country a lot, which is really fun.
You are so adventurous. I don't know if I could do that. Like just going to a different country where English is not the main spoken language, I would be so intimidated.
It is definitely
very brave. It's very brave of you to do that. Wow.
Yeah, at least here in Finland, almost everyone speaks English, which has definitely made it a bit easier. Okay, for me.
Well, that's a country I could maybe go to. I only speak English. That's it. But my wife and son speak English and French. So that opens up a few more countries we could go to.
Yeah, I'm trying to learn Finnish, but it is honestly quite slow going because it's a difficult language for me.
It sounds difficult. So you've moved around Europe and you've pursued this doctoral education path. What got you into science? Like, what was the thing? Because getting a doctorate and then doing that's no joke. You have to really love what you're doing. What got you into science?
So when I was a young kid, one of the first things I learned to say was, "What's that?" So I would run around the house pointing at things like, "What's that? What's that? What's that?" And my parents would give me answers. And at some point, they realized that they couldn't answer me anymore because I was like pointing at random things like, "How does a TV work? What's that?" And it's like, okay. You're going to have to figure this out yourself. So then I realized that going into science was the way to answer these questions of what's that. The more I studied science and physics, the more I realized that, you get an answer to one question and that just opens up 50 other questions and 50 new things that you don't know about. And it's this constant feeling of discovery and curiosity. And at some point I realized if I wanted to answer some of the big questions, like looking out into the night sky, what's up there, what's that? To answer those questions, I needed to become a cosmologist, which is what I do these days.
Right. And you know what? We were talking before we started recording about you being a cosmologist, a theoretical physicist, but a cosmologist. And I was lamenting that perhaps folks confuse astrology with cosmology, but you said sometimes something else gets confused with cosmology.
Yeah, I have been asked before if I'm a cosmetologist, which is someone who studies makeup. I can understand where this comes from because cosmetology is perhaps a word that people hear more. Whereas perhaps for my job, people hear more the term astrophysicist. So sometimes I will call myself an astrophysicist, but there is a bit of a difference, and I focus more on the cosmology side than the astrophysics side.
So would you be able to explain the what does that mean? Because I don't know. I'm sorry.
No, it's perfectly fine. They are both branches of theoretical physics, and they are both branches that study the universe. But I think the big difference is that cosmology studies the universe as a system and like the whole thing, whereas astrophysics is usually more the things inside the universe. And one analogy that I like to make often is if you consider an ocean with all of the animals living inside and all of the ecology that you have and the environment that you have inside the ocean, you might say that a cosmologist is the person who studies the ocean, while the astrophysicist might study the species inside the ocean. So it's slightly different here. It's like a cosmologist will focus on the universe as a whole concept and things inside the universe, whereas astrophysics is more the individual parts. But of course, the line between them is quite blurred because it's very easy to move between astrophysics and cosmology depending on what you're doing.
Gotcha. Well, you know what? I just learned something new. I always stay quiet when my guests are like, I'm a cosmologist, and another one will be like, I'm an astrophysicist, and I'm like, I kind of feel those are the same thing, and I just stay quiet because I don't want to appear stupid. Thank you for explaining that.
No, I always have the idea that there are no stupid questions, and this is how we learn things, is by asking questions.
Too true. When you were young, did you look up at the stars in the night sky? Was that part of the wonder of studying space and the cosmos?
It was actually. I remember some days being out with my dad where he would point at random stars and tell me how to find them and identify them. And I loved just looking up and feeling, when you look at the stars, you just feel so small, but also connected somehow to space. And when I started studying physics at university, I actually joined an astronomy club and got a telescope. And looking through the telescope at the night sky, that was really made me realize like that is what I want to study. Those things out there that we can only see a fraction of, that's really what I want to understand.
Figuring Out Family isn't your ordinary podcast. It's a completely new experience that helps you make your family the best it can be by giving you the deep insights to help your family thrive. You'll learn how to help your family have more productive conversations and manage life's disappointments too. You'll feel inspired by the special guests that are experts in their field of family relationships. Get valuable tips for dealing with difficult family members, repair broken relationships, improving your parenting skills, and keeping your children happy and healthy. Check it out now.
Wow. And then through the math you study, you can answer the questions to what's going on up there.
Well, we try to answer these questions. We don't always find answers.
We're going to get into that, right? A little bit. Yeah. I love it. Since you study the cosmos as opposed to specific things in it, do you still get excited about, like pictures being back from Mars or like pictures being back from Venus or what the Webb telescope is going to get us specific things in space? Or are you like, okay, that's nice, but I need to know more about what's going on in the whole system?
I think anytime we get images like this, I love them because it's just such an incredible feat that humankind is able to do this. Like we send robots to other planets and they send us back photos. It's cool. And I'm very easily excited by anything space related. So sometimes like we'll get a new image from the Hubble Space Telescope. It's like, that's really pretty. It's not something I'm going to use for my work directly, but look, we have a picture of space and this is amazing.
You admire it, but you admire it because it's so amazing. Yeah. Specifically to things you study, let's get right into it. And the first one is gravitational waves.
Big topic.
What are they?
So gravitational waves are one of my favorite things in the universe. They're also one of the tiniest things in the universe, which is fun. So gravitational waves are ripples in the fabric of space-time. So from general relativity, we know that space and time are not separate concepts. They are intrinsically connected in space-time. And if you consider a person moving through a swimming pool or in a lake or at the sea, you create ripples in the water. Now, things in the universe can do this to space-time. If you have a very dramatic event in the universe, like two black holes smashing together, this can actually create ripples in space-time itself. And these are basically ripples of gravity. And this is what we call gravitational waves. Now, the cool thing about gravitational waves, if I say like ripples in space-time, it doesn't really make sense.
Like what like space-time is a thing, but it's not obviously water.
Yeah, obviously not. But the cool thing is you can have these distortions. These like what we're basically doing is we're having a place where space-time might grow and it might shrink. So one way to think of it is if a gravitational wave travels through you, it will make you grow and shrink in one direction and then do the same in the opposite direction when the next part of the wave hits you. So if a gravitational wave travels through you, first you will get taller and thinner, and then you will get shorter and wider. So
I don't like that. I'd like to be taller and thinner, please.
Yeah, the problem is you can't really use gravitational waves to become taller in practice because it's a really, really, really small effect. If a gravitational wave goes through you, you would grow by 1/1000th the width of a human hair. So, but really,
so this is not helping people achieve their like height dreams in the NBA.
No, definitely not. You'd need quite a few gravitational waves stacked up, and you just really aren't going to get there. It's like,
and then I think, would you die? Would it like stretch you apart, or would you just be okay because everything gets bigger?
Everything gets bigger. That's the thing. And
whoa!
This is also the problem because if we want to measure something, usually we take out a measuring device like a ruler.
Yeah.
But what do you do when your ruler is also getting bigger and smaller? Then we have a problem with measuring gravitational waves. The solution we've actually found to this is to use lasers, which is mind-blowing to me that we use lasers for this. But the idea here is that light will always travel at the speed of light. Regardless of what you're doing, how fast you're moving, light will always, always, always travel at the speed of light. So this is a universal constant. Which means if you send a laser beam traveling down a tunnel, and this tunnel shrinks or grows because of a gravitational wave, the time it takes light to travel through the tunnel is going to change because its speed is still the same. And we know that speed is just distance over time. So if the distance changes, the time has to change as well. So by measuring a time delay in this laser beam going down a tunnel, we can actually tell if a gravitational wave has passed through the tunnel. Which is still amazing to me to think that we just use lasers to measure gravitational waves.
Lasers, what can't they do?
Right, exactly. This is really nice because everything we do to study the universe up till we had gravitational waves, or up until we figured out how to measure gravitational waves, we normally use the electromagnetic force. So we have electromagnetic waves. Anything light. So everything from like X-rays to microwaves, these sound like different waves in the universe, but they're all just part of the electromagnetic spectrum. So they're all just visible light or different types of light. Whereas with gravitational waves, it's a completely different way of being able to study something in the universe. And one example we can use here to really appreciate what we can do with gravitational waves is to think of the case of two black holes smashing together. So black holes are objects in the universe that do not emit any type of light. They're too dense. You'd need to travel faster than light to escape a black hole. Nothing can travel faster than light, so nothing escapes a black hole. So it also means
what happens in a black hole stays in a black hole.
Exactly. Nothing comes out of there. It's a good place for privacy. But the cool thing...
Never-ending, infinite privacy. It's good for introverts, I guess.
Definitely. So... It's very difficult to study black holes because we cannot directly see them. We can only see their effects on objects around them. But if you have two black holes smashing together, this is going to produce gravitational waves. And then if we can measure these gravitational waves, we can understand how big these black holes were, how fast they crashed together, why they crashed together. This is really cool, and this is actually something we have done. Thanks to the LIGO and Virgo detectors that we have here on Earth, and now the CAGRO one as well, we have now measured over 90 collisions of either black holes on black holes, two neutron stars smashing together, and even a neutron stars and black holes smashing together.
Wow.
And this is something
you would never be able to detect this before. Like this is you without this you can't tell that
without the gravitational waves. It's very difficult to study black holes. So with gravitational waves, with the first detection, we were able to say for sure that black holes exist because this was the first direct evidence. We had a lot of indirect evidence of black holes, but now we can say for sure black holes exist and they crash together. And we've seen this happen over 80 times by now, which is really cool.
Amazing. Now, okay, so these gravitational waves are so tiny, so you need like extremely sensitive lasers.
Yeah.
And they're happening, like this is happening really far away. So this ripple, does it travel forever? Like, does it run out of steam like a wave might run out of steam?
So it does travel kind of outwards from the events, from the merging black holes, for an example, and it will gradually be redshifted. So it will be stretched slightly as it travels through the universe. So we say redshift when something gets stretched in the universe, and it will gradually get stretched and get slightly weaker. And by the time it reaches us, it's this like tiny, tiny, imperceptible thing that is really difficult to measure. But we can look at this and say, okay, like 1.5 billion light years in that direction in the sky, 2 black holes crashed together a couple billion years ago, and we're just picking this up today.
What? So if you were closer to 2 black holes colliding, would the wave be bigger?
Oh, I always struggle with that question. It would be slightly bigger, yes.
Okay.
But if you were that close, you'd have other problems.
Yeah, that's what I was going to say. Like, you're going to have other issues being that close to black holes colliding.
Yeah, definitely. But something that I love about gravitational waves, so they allow us to study black holes, which is amazing. But this is just really the tip of the iceberg. And these are actually the biggest gravitational waves. But there's other gravitational waves that are even harder to study, which are ones produced by the universe itself. And here's where we go into the weird stuff. So
let's get weird.
In the early universe, we're pretty sure that the universe experienced what we call inflation. So the universe grew exponentially. It went from being very small and very hot to being very, very, very big in a short amount of time. And this is what we call inflation. And this is a dramatic process where all of space-time is being stretched. It's quite likely that this process produced gravitational waves as well. And these gravitational waves today would make up a background. In every direction you look in the universe, there should be this background gravitational wave signal. And then there's other things in the early universe, like we know that the universe was cooling down. And if this cooling down happened in patches where you had some hotter and some colder patches, that you had kind of bubbles of hot regions in the universe and bubbles of cold regions, if these could collide together, they would also produce gravitational waves. So if we could measure these gravitational waves, we could understand the very first seconds of the universe. And
you can't do that with light. Because our telescopes just can't see that far back in time. Even the James Webb, I read, like does really good, but it's still millions and millions of years. There's going to be incomplete data.
Yeah, I mean, that one's going to look about 8 billion years into the past. I'm talking here about the first second of the universe, so it's almost 14 billion years ago.
Oh my goodness. That's a big difference.
It's a big difference. These gravitational waves are so difficult to detect. You can't do it from Earth because there's just too much getting in the way. There's too many background noises that make this difficult. So what we have to do here is to send a mission to space to actually try to measure these. And there is a mission planned for this, which is the LISA mission. Now, LISA is basically going to be 3 spacecrafts kept in a perfect triangle that are going to be chasing the Earth. And they're going to be bouncing lasers back and forth between each of the spacecrafts and using the same technique of measuring how long it takes the laser to bounce back and forth. They're going to look for these early universe gravitational waves. And LISA is set to launch in the next 15 to 20 years.
Oh, boy. Okay, so that you need this technology to answer the teeny tiny gravitational waves.
Exactly. And this is actually what I'm working on and a lot of people in Helsinki are working on. Because if we send out this LISA mission and we get a measurement of this background of gravitational waves, we want to know what this tells us. So what my research is these days is asking the question of, if LISA measures something, how can we then use that to understand this first second of the universe? And for that, we first need to make very accurate predictions of what we'd expect to see based on different understandings of this first second of the universe. So a lot of what we do is basically throw all our knowledge at a computer and get it to simulate what these gravitational waves would look like, so that we can ask the question of, will LISA actually see these?
Hey everyone, and welcome back to Queens on the Road podcast. This is Latavia here. This podcast was created to educate and inspire people about the ably different community who are on the move.
So come roll with us. We educate and have a little fun too.
Is that I have something that is called a helix vulgus, which is like a bunion that people with CP get on their feet.
Putting me on the spot.
Yes, I'm quizzing you now. What is my favorite movie? I'm putting this friendship to the test.
Yeah, because you wouldn't want to send 3 expensive spacecrafts to space to have them not be able to detect what you want them to detect.
Exactly, and to not be able to understand the data when we get it. So we still have 15, 20 years to be ready.
You got time.
You
got lots of time.
That's my life plan.
Yeah, but what an amazing, like, you'll be even further in your career and you'll have all of this knowledge when this data comes.
Yeah, we really hope that by the time LISA launches, we'll be ready to clean the data, to process it, to understand it, and to answer the questions of like what happened in the first second of the universe, or even the first fraction of a second of the universe.
Wow. That is pretty profound.
It's pretty cool.
Yeah. Okay, so my mind and brain are jello, but I have another question for you. You study cosmological tensions.
Yes.
And I Googled this to try to get some kind of background, because I do that before I speak to guests. And I don't know. Could you help me out with what cosmological tensions are?
Sure. So one big thing in science is being able to answer the same question multiple times. Usually what you want to happen is that if you ask a question different ways, or if you make a measurement different ways, but you're measuring the same quantity, you should get the same result. If you don't get a result, if you do a different experiment to measure the same quantity and both experiments give you a different answer, then you have a problem. And this is what we call a tension. And depending on how different the answer is, it is more dramatic or less dramatic. Now, if you do a measurement in 2 different ways and you find an answer that is very, very close together, you say, okay, they're not perfect, but it's close enough. But if you find something that is statistically very unlikely to be able to be explained, then we have a problem. This is what we call cosmological tension. So it's when 2 different data sets are in tension with each other. They don't give the same answer. Now, the biggest one we actually have, or the most well-known one right now, is what we call the Hubble tension. Now, there are several different ways we can measure how the universe is expanding. We know that the universe is currently expanding and that this expansion is accelerating. And you can measure the rate of expansion, or the expansion rate, which is what we call the Hubble rate, or the Hubble constant. And there are a couple of different ways you can measure the Hubble constant. One of them is using the background light left over from the Big Bang. So this is light that was produced 380,000 years after the Big Bang, and it really is the afterglow of this initial expansion. So you can measure this, and then from there you can make a prediction of how fast the universe should be expanding today. This is what we call using the CMB, the cosmic microwave background radiation, which is its background radiation. And there's another way you can measure the expansion rate of the universe, which is looking at exploding stars close by, which are supernovae. Now, the nice thing about supernovae is that they release the same amount of light, so you know how bright these should be. So by looking at supernovae in the night sky and seeing how much light we receive from this supernovae, this exploding star, you can try to figure out how far away it is from us and how fast it's moving away from us. So this is what we call the local measurement of the expansion rate of the universe. And now, if you compare these two, one of them is like an early universe prediction of what's happening now, and the other is a current observation. Right. And if we've done everything correctly, you'd hope you'd get the same number.
It should be the same early and the same now. Yes, gotcha.
Yes, you'd hope so. Now,
you'd hope so. Uh-oh.
You'd hope so. But what actually happens is that from the early universe measurement, you get a value of about 67.5 plus minus 5. This means that it's somewhere between basically 66 and 67. Sorry, between 67 and 68. And if you do the measurement from the supernovae, you get a value of 73.0 plus minus 1.
Uh-oh.
Now, the plus minus here is important because if one of them is like 65 plus minus 15 and the other is 70 plus minus 15, that plus minus 15 is our degree of belief in the measurement, and they would still be overlapping.
Exactly. Yeah, we teach that in at school with the high school kids. With in chemistry, it's your error propagation.
Exactly. It's just your degree of belief in the measurement. And
exactly. Yes. Cool.
Yeah.
Okay.
Yeah. So the problem here is that from one we're getting like 67 plus minus 0.5, and from the other we're getting 73 plus minus 1. Now, these are close. I mean, one of them could have given us 500 and the other could have given us 2. So they are very, very close, but they're not quite close enough. This is a problem because we would hope that these numbers would agree. Now, there are several possible explanations for why they don't agree. This is collectively known as the Hubble tension, and it is one of the cosmological tensions. So there are several different explanations as to why these numbers might not agree. First of all, you could say maybe this is a statistical fluke. You know, maybe if you do the experiment another few times, this might go away. Mm-hmm. But if you look at the difference between the numbers and the error bars, as we were saying here, it's quite a big difference. It would basically be a 1 in a billion chance of this being a statistical fluke. Another possibility is that there's a mistake in one of the measurements. Either the measurement of the early universe background light is wrong, or the measurement of the supernovae is wrong. Now, the cool thing is, a lot of different experiments have redone these measurements. So there's a lot of different people who have done the supernova measurement, and the CMB measurement has been done by several different collaborations. Okay. And all of them find the same self-consistency. So the CMB measurements all agree, the supernova measurements all agree, but they don't agree with each other. So this means that it's not so likely that it's a mistake in one of the measurements. So then we come
So it's some other third thing.
Yeah, so then there's the other option, which is that one of our assumptions is wrong. Now, there are assumptions that go into measuring the supernovae, like the fact that the brightness is the same and that we can understand this and that we can model supernovae. And more interestingly, for me at least, when we do the measurement from the early universe, this part of the measurement of this background light in the universe is something that is well understood. But then when you take that light and you make the prediction of the expansion rate today, you need to use a specific cosmological model. And this is what we call our standard model of cosmology. And this is basically our current understanding of the universe based on all of the data we have. Now we have to ask the question of, what if this standard model of cosmology is wrong? What if there's something we've missed? And what a lot of people do is try to change this standard model of cosmology in a way that you can solve this tension, that you can bring these measurements back into agreements. But this is very difficult to do because our standard model of cosmology is supported by hundreds of different observations spanning decades or billions of years across the history of the universe. We have measurements from the first few minutes after the Big Bang up until today. And all of this supports the standard model of cosmology.
Dang.
So the fun game we get to play now is, how can we break our standard model enough to solve the tension, but not too much so as to mess up something else?
You throw dark matter and dark energy at it, right?
Yeah, that is one option. And that is actually...
Oh, okay. I don't know. That, as a layperson, I'm like, that is how you explain things in space that don't make sense.
Yeah, the thing is, our standard model of cosmology includes dark matter and dark energy.
Oh, okay. Whoops.
No, but a lot of what I've actually worked on is asking the question, what if dark matter isn't as invisible as we think it is? Or what if dark energy can talk to dark matter? Would this solve the Hubble tension? And the answer we always find is no. Whatever you try, you mess up something else. Currently, nobody's found a complete explanation for the Hubble tension. There are some models that seem to work, but then they break something else.
So it's the butterfly principle.
Exactly. You can't really, you just change one small thing and suddenly your galaxies look completely different. So this is not the only tension we have. There's also a tension in how matter behaves on small scales, but it's not as dramatic, or the difference between the measurements is slightly smaller. But one good thing about this cosmological tension, this Hubble tension, is that it really makes us revisit all of our assumptions and all of our measurements. And there is hope in the future to solve this in different ways. And I can actually tie this into what we were talking about before. Because if you have two neutron stars smashing together, you produce gravitational waves, but you also produce a burst of electromagnetic radiation, so a burst of light. And if you measure these two things simultaneously, which we have already done once, from the light you can measure how far away the neutron stars are. And from the from the light you can measure how they're moving away from us. And from the gravitational wave signal, you can measure how far away it was. Which means you can actually use gravitational waves to get a measurement of the expansion rate of the universe. And this is completely independent of supernovae, independent of all of our assumptions, and independent of how we measure the light in the early universe. So this is a third way of doing this measurement that might shed some light onto the cosmological tension.
It could be the puzzle piece you're missing.
Exactly. And from just one observation of two neutron stars smashing together, they were able to get a measurement. And their measurement was 70 plus minus 10, which is smack in the middle of the other two.
It is.
But it's plus minus 10, so it's somewhere
plus
between
minus
60
10 is
and 80.
Not great, yeah.
Yeah, the problem there is we only had one, but it's expected that within the next 10 years, we should get about 100 of these. Yeah. This might help us answer the question of, is either of these measurements wrong?
It's so wild that even in something where you have all of these super intelligent people that have devoted their life to it, like the study of cosmology, there has to be something wrong with one of the assumptions made. Like there just has to be. There has to be something wonky, right? That's the only way to explain it.
And this is where sorry.
Yeah. Oh, I'm just saying, and for somebody like you, that when we started our interview, you were the little kid that asked why. This would be fun for you, but not. Whereas for me, it would be frustrating.
Yeah, it's a bit of both, really. I like when my science is consistent, but also when things don't work, that's where the fun starts, because then you get to go back to the drawing board like, okay, what did we miss? What did we do wrong? How do we fix this? The data doesn't lie. If the data tells us that one of our assumptions is wrong or that one of our theories is wrong, that's how we progress science, by changing this, by following the data.
Yeah, science doesn't lie. It just doesn't know.
Exactly. It doesn't have all the answers. And the day it does, we run out of fun things to do.
I don't think that's ever going to happen.
Oh, definitely not.
No. At least I hope it doesn't happen. I'd be out of a job with my podcast, I guess.
Yeah. And the day we understand everything, I think that would be very frustrating for me, because I love the discovery of science. And I like that there's so many things we will never discover.
Okay, so I'm going to pick my brain up off the ground because it's a puddle of goo. So we ask all of our guests a couple standard questions on the podcast, and one of them is to share a pet story with us. Would you be able to share a pet story with us, Doc?
Sure. So I currently don't have any pets because I move country so often that it just wouldn't be fair to have a dog or a cat. But growing up, I actually had a husky. My family had a husky. She was called Nala. And as I'm sure you know, huskies have very big personalities. They're slightly stubborn, slightly argumentative, but also great dogs. So our husky, Nala, always liked to be very proud and elegant, and she always looked graceful. But she also had her stupid moments, and those were always very funny because they contrasted with like this nice, elegant husky image. There was one day where my parents were walking the dog in the forest, and she started stalking something like there was an animal, and we were always careful to keep her away from wildlife. But this was the day after Carnival in town, and we realized that what she was chasing my parents realized what she was chasing was actually a wig that somebody had left behind in Carnival. So it was this big black hairy wig. And the husky decided it was something she had to catch. So she chased the wig through the forest in the wind, and she managed to catch it. And
Yay!
She was very proud of herself. So she carried it all the way home through the town. So you had this like nice, pretty husky with this black carnival wig in her mouth. Then she got home and lost interest and left the wig at the door to my house. And then I got home from school and just opened the door and there was this black hairy thing on the floor. So it freaked me out, like, oh my God, what is this?
Yeah, exactly. Yeah.
So that's how we ended up with a random carnival wig in our house after she'd walked it through the whole town. And then she went on like, yeah, such a proud husky, but she basically chased the wig and managed to catch it. So,
why would you not be proud? That seems like a great accomplishment for a dog.
Yeah, definitely. But we were always amused. And then anytime we saw anything blowing in the forest, it's like, is that a wig? Is she going to chase a wig again? She also did the same with a mop once. It was just anything that moved. Goodness.
Looks like a little hairy critter she's got to go get, I guess.
Yeah, and you'd think they'd have good sense of smell and be able to tell when they're chasing a wig, but apparently not.
And maybe it was just fun. You never know.
Yeah, maybe she just wanted to embarrass the owners by carrying this wig through the town.
That's true. That is an adorable story. Thanks for sharing. So the other question that's standard, and I'm not sure how you're going to top what we've been talking about, but it's called the super fact. It's something that you know that when you tell people, it blows their mind a bit. And wow, I'll leave it to you if you've got anything left there, Doc.
Yeah, so this is actually one of my favorite facts about the universe.
Okay.
Now, you've probably heard, and a lot of the listeners have probably heard the phrase from Carl Sagan that you're made of stardust.
I love that.
Yeah, this is because the carbon atoms in your body, the oxygen in your body, a lot of the heavier elements were actually made in exploding stars. But I think it gets cooler than that, because that doesn't answer the question of where does the hydrogen come from. Now, 10% of the atoms in an average human are hydrogen. And the cool thing is, all of the hydrogen in the universe was made in the first few minutes after the Big Bang. So all of the hydrogen in the stars, all of the hydrogen in us, all of this was made 3 minutes after the Big Bang. And this means that 10% of your atoms are universe dust. And 10% of this 10% of your atoms are nearly 14 billions of years old.
We're so all connected even more.
Exactly. And this is why I love this, apart from the fact that it's mind-blowing that you have like 14 billion-year-old atoms in you. You know, the universe is huge and it can be overwhelming and scary, and there's a lot of stuff out there that we don't understand. But I find it very comforting to know that we carry a part of the universe inside us and that we are intrinsically connected to the universe. The fact that we are stardust and we are also universe dust, to me, is somehow comforting. I love thinking that some of my atoms are so old.
It doesn't help if you wanted to get, alcohol at an earlier age, though, right?
No,
you still need to have your driver's license.
Yeah, I think
we can't say my atoms are actually over the legal limit.
Yeah, at that point, it's like, well, only 10% of your atoms, and we need 100%.
You need 100%. Gotcha.
Yeah.
That is a fantastic super fact. I have never heard that one before, Deanna. Thank you.
Yeah, I love that fact.
I read a paper recently. It's probably an older paper, but it was new to me, that the astrophysicists are pretty sure that elements heavier than iron actually aren't from supernova, but from neutron stars colliding in some bananas collision of that weird nuclear, like what is it called? Nuclear pasta? Yeah. Something's bizarre in neutron stars. And when it smushes together, that's how you get like tungsten.
Yeah.
And some of the heavy elements, right? That's true? Is that true?
That is true. And one of the ways we've actually been able to test this is using the gravitational waves that came from
gravitational waves, yeah.
Gravitational waves. When the neutron stars smashed together and we measured the gravitational waves, we were able to see how much gold was produced in that collision.
What? No. Really?
Yeah, 3 times the weight, or 3 times the mass of the sun, of the Earth, in gold was produced when these 2 neutron stars smashed together. We
got to go out there and get that gold, Doc.
Yeah, it's a bit far away.
I know. That's the thing is I tell kids stuff like that and they're like, we just need to go get all that tungsten. Yeah. And I'm like,
if it funds space missions, I'm on board.
Yeah, it's like millions of years away, guys, and we can't get the speed of light. We're talking like we'll never get there.
In fact,
Like it might, that wherever it's from might be moving faster away from us than we can fly. So we'll actually never, ever, ever get there.
Yeah, depends how far away it is, and depends how fast the universe is expanding, which we're still trying to figure out.
Oh my goodness. That is a super fact. 2 thumbs up. 2 thumbs up for your super fact. So the last question and the last area of the podcast is the important to you section, emphasis on paw, where guests get to talk about hobbies or causes that they are excited about. And you wanted to talk about your science outreach through your YouTube channel. Go ahead. What is it about? What's going on there?
Right. So one of the things I love about science is being able to share the amazing things that we learn with everyone. And I think science really should be for everyone. And this is one of the reasons I love the Bunsen and Beaker podcast and Ginger, because it's really bringing science to more people. And one of the ideas that I've always had is to break the idea of scientists being this lone genius, this unapproachable person. And I hope to convey that scientists are just everyday people. We're just like everyone else. We're not special. We're not geniuses. We're just people who happen to have the privilege of studying science. So about 6 years ago, I started Cup of Cosmology. Now, Cup of Cosmology is a live streaming show where I try to answer all of the cool questions that people have about the universe. The only rule here is that there are no stupid questions. It's a judgment-free zone. And I'm online every week. You can find me on YouTube. And if you Google Cup of Cosmology or go to cupofcosmology.com, you can find all the information.
I'm doing that right now. Cup of Cosmology. I'm doing that right now.
So usually once a week, I do a live stream where anyone in the world can come in and ask me questions about science, about the universe, without judgment. And my idea here is that a lot of people have just never had the chance to speak to a scientist. And what I hope here is that people can ask their questions freely without any judgments, without me saying it's a stupid question. And I will always just try to give an answer. I get guests to come on and help, and I pick topics, and this has been going on for 6 years now. So if you have any more questions about the universe, Cup of Cosmology is the place to get your answers. And I really try to get to everybody's questions. And I hope that this will just take one step towards making science more accessible to people and hopefully making science more inclusive.
I love that. I am watching like one of your, it must be like a best of Cup of Cosmology. You're using HAPS.
I was using HAPS.
Okay, all right.
HAPS closed down in May this year.
A while ago. That's where, like, this is a bit of a side. That's where a lot of Spaces hosts came from. They were HAPS hosts, and they moved to Spaces.
Yeah.
And okay, so you run this. You run this on YouTube once a week.
Once a week, usually every Sunday at 7 p.m. Central European time.
Okay, all right. I'll have to figure out what that is my time. I would love to come to one of these.
Yeah, I'm usually online every Sunday. If I miss a Sunday for life or something like that, I always tell people.
7 Central European time.
On the webpage Cup of Cosmology, there is a time zone converter, so you can get it in your own time zone.
Right, because oh my goodness. Okay, that's so cool. I might tweet that link out just as a tweet.
Oh, please do.
That's so cool, Doc. Oh, you're so animated when you're talking. I love it. I can't wait to. That's one of the things, this audio is great because you can be listening to this while you're mowing your lawn, on your commute. Or cooking, right? Cleaning, walking your dog, whatever, right? But it is cool to see you talk with such passion.
Yeah, I think because I also I grew up in Spain in the Mediterranean, and I actually do talk a lot with my hands.
Oh, you talk with your hands?
Throughout this podcast, my hands have not stopped moving.
I've heard you clap a couple times when you've been talking to make a point. Yeah.
My hands are just constantly moving, and then with the video, people can actually see that a bit more. When I'm talking about the expansion of the universe, I'm doing visuals with my hands. So I like podcasts because, as you say, it's a freedom to listen wherever you are. Yep. But for me, I think visual works better just because I can convey my enthusiasm a bit more.
Oh, I get it through your voice. I've been getting I get ripples of goosebumps all over my body when I talk to guests, and I can just hear the passion in their voice for what they're studying. I just get this. I was like, oh, I'm so privileged to talk to people like you.
Thank you.
We'll make sure the link to your YouTube channel is in the show notes and also your website as well. Awesome. So folks can find it there. And I think before this comes out, I'll just tweet out that link too, because that's super cool.
Sure. Thanks.
We're at the end of the podcast interview. Dr. Hooper, thank you so much for giving up your time to talk to us today.
Thanks for having me.
This was so great. Are you on social media? Can people follow you on Twitter?
I am. I'm DC Hooper 91 on all social media. I say all,
Okay.
I'm mainly on Twitter. So
Gotcha.
on Twitter, DC Hooper 91.
Okay, you take care of yourself. Best wishes in the future.
You too.
Hello there. It's time for story time with me, Adam. It's time for story time. If you don't know what story time is when we talk about stories that are oh God. Story time is when we talk about stories that have happened within the past 1 or 2 weeks. You know what, Mom? Do you have a story of what just happened?
Hi, this is Ross, the host of Smells Like Humans, a show about interesting and quirky human behavior. We bring humor, empathy, and warmth to topics such as relationships, dating, work, self-compassion, weddings, phobias, aging parents, travel mishaps, death, and many more. Ever wonder what happens at a cuddle party? We talk about it. Free-range kids in restaurants? We've got some thoughts. Bedtime stories for adults? We're on it. Light, fun, unscripted conversation and personal stories. Please join us by clicking the link in the show notes.
Hello, everyone. I sure do. So you may or may not know, and you probably don't because I don't advertise it. I am getting my teeth fixed using a product called Invisalign, and it makes me hiss a little bit. So I decided to take the top Invisalign out, and it wasn't coming out. So I was trying to be all sneaky, like you're supposed to be able to go click, click, and then it comes out. It wasn't. And it was actually stuck in my face. And I looked at Annalise, and she laughed at me. And then Adam could not stop laughing. But Adam also has had Invisalign, and he's done his. So he just wears a retainer. So he knows the pain of Invisalign when it doesn't quite work properly. So that's the story of what just happened. Thanks, Adam.
Dad, do you have a story that happened within the past 1 or 2 weeks about the dogs?
Okay, I'm kind of hoping, Chris, you have an actual story about the dogs. I will talk about, it's been fun to shoot. It hasn't done well on TikTok, I'll tell you. I've been trying to grow the Bunsen and Beaker account on TikTok, and I've had some success over the last month. But one thing that hasn't done well at all are my live texts from Bunsen. They've been really fun to make, and they've done pretty good on Twitter, but I think they're just too weird for TikTok because people don't know what's going on. But my story is, it's just been fun to shoot them. The text from Bunsen is this joke we do every week. I come up with 4 jokes of Bunsen texting different people. And I found this website that allows you to do live texting stories. And I kind of like intercut it with footage of the dogs and me. And the next one's going to be actually one of the Adam texts. And it's been really fun. But sadly, nobody on TikTok likes it. So if you're on Twitter and you liked one of the live action texts from Bunsen, thank you. They do take a while to make. I think I'll make a few more, and then that's the end of it. But anyways, that's my story. Oh, by the way, Bunsen's such a good boy for text from Bunsen. He's really easy to get to do the stuff for text from Bunsen, even grabbing his paw and and pretending he's texting a phone.
All right, I have a story. Ginger, if you don't know, Mom likes to buy Ginger a bunch of toys, and a lot of them make sound. There's this bird. Hold on, let me get some of the toys. 1 second.
It's going to be a show and share, but no showing, just sharing about the toys that I buy Ginger. And in the store, Adam always damages my calm because he's like, Mom, don't buy that. Mom, don't buy that. Ginger doesn't need that. Ginger doesn't need that. Mom, don't buy that.
I need like an intermission sound.
An intermission. No, you need a sound that's like, please save Chris from herself sound. Do you have that sound?
No.
No. Well, there needs to be
This
that
day
sound
is
because
bananas. Bananas. This day is bananas.
That's the best I have.
that's not it. But you can keep trying.
Okay.
Yeah, and Ginger uses none of the toys that Mom has bought her. Ginger is not a toy type of cat unless you play with her with the toy. Anyway, we have a bird here, and it makes a sound.
Oh, there it is.
So what happens is that one of the dogs, Bunsen or Beaker, plays with the toy and it goes in the corner, and it doesn't stop because they like chew it, and then it's every bite it does the thing, and it's super annoying because Ginger doesn't play with it. Ginger doesn't play with it at all. But there's this other one, and it like squeaks when it hits a surface. So you like smack it and it goes, it tweets, it has like a tweet sound, and it hits a surface and then it makes that sound. And if it hits another surface, it makes the sound again. And there's no lag in between them. So it can do it like instantly. But now, I don't know what happened with the toy, but it thinks it's hitting a surface constantly. It thinks it's constantly hitting a surface. So it sounds like an alarm that you have in your house for when a burglar like gets in. Oh, when I came home today, I thought someone had like tripped our home security system. 1 second.
He's going to go find this toy that's making this out. He's hid it because
there it is.
It's the Princess and the Pea.
I thought an alarm was going off in her house, but it's just a Ginger toy that doesn't shut off.
Yeah, so I put it under blankets, and I could still hear it.
And yeah, Bunsen doesn't like it. He takes it away. Safety Officer Bunsen will take that toy away.
This is one toy that Ginger actually likes playing with, but it is so annoying. And Beaker also really likes it. But yeah, Mom, do you have a story?
I sure do. My story happened on Wednesday this week. I took the dogs to doggy daycare because that's what they like to do. They like to go there. And we were traveling. It was a normal route until, dun, 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 we were going to turn on the road that the doggy daycare is on. There was a train. And so it was going ding dong, ding dong, ding dong, ding dong, like the train track sound. And the arm was down and the lights were flashing. And Beaker was like, oh, I've never seen this before in my life. And so she watched as the train cars went by and kept going and kept going and kept going. She was very curious about the train on the train tracks. But we were safe in the car at a safe distance away from the controlled stop. And that's my story.
That's so weird. That's the first time that Beaker's seen a train. That must be weird to a dog, though. Really, it's like a giant metal snake that's just going. And Beaker's never really seen a snake either.
All right, so that's story time with me, Adam. Yeah, I'll see you guys on the next podcast. Bye-bye.
That's the end of another Science Podcast episode. Thanks for coming back week after week to listen to our show. Special thanks to our guest, Dr. Deanna Hooper, who talked to us about the cosmos. That was out of this world. Hey, it's an ending pun. We'd also like to give a shout out to the Pawpack. The Pawpack patrons support us, and man, thank you so much. We've been able to use your support to reinvest into things like the upcoming Pawpack community. Stay tuned for that. All right, let's hear their names, Chris.
GBLB, Tracy Domague, Anne, Julie Smith, Sharon Dotson, Andrew Lynn, Elizabeth Parmentier, Peggy McKeel, Sandy Breimer, Tracy Hallberg, Jenny Jaguar, Chris Kelly, Leela Perriello, Sam, Catherine Jordan, Donna Craig, Debbie Anderson, Courtney Proven, Renee Hardy, Jody Ogren, Mary Ryder, Shelby Leggett, Mary Coos, Marianne McNally, Elizabeth Bourgeois, Karen Beth St. George, Liz Button, Kathy Zerker, Ben Rathert, and Bianca Hyde.
For science empathy, and cuteness.